All right, we are going to start talking about gas laws, and we are going to start with what we call the ideal gas law. In most textbooks, including your textbook, this is the last gas law they talk about. However, the reason they do that is because the other gas laws were developed first historically, and the ideal gas law came out of those other gas laws. It doesn't really matter that this was the last gas law developed. It's the most important. It's the one we're going to use the most, so it's the one I'm going to talk about first. Okay, the equation for the ideal gas law, you guys probably are all familiar with it from other chemistry classes. PV equals nRT. All right, so let's talk about each one of those things individually. P is, I'm glad I erased that. P is pressure. And the units can be any unit of pressure. Atmospheres, we can do millimeters of mercury. We can use any unit we want. V is volume. Usually liters, but sometimes we do milliliters. N is moles, and it has units of moles. Leave the E and the S off of it to save us drastic, or lots and lots of time, not drastic, lots of time, lots of time. T is temp. Temperature always has to be in Kelvin for gas laws. Otherwise, think about it, if you plugged in a 0 for temperature, you could solve for 0 moles of a gas taking up a volume, and that would make 0 sense. All right, and then universal gas constant. It has lots of different names. Ideal gas constant. It doesn't really matter what you call it. I'm going to call it the universal gas constant because that's what I'm used to calling it. And it's called a proportionality constant. Basically, it just makes the two sides equal to each other. And I put the arrow to the wrong thing. That's R. All right. It just makes the two sides equal to each other, and it has to be there. And it can have different values depending on what units you are using. So one of those values, the one I tend to stick with, 0.08206. The units are liters times atmospheres over kelvins times moles. Okay. It does have, remember that liter atmospheres can be a unit of work. So we get this other strange, I don't know if we're going to use it in this chapter or not. In past semesters we've used this. 8.3145 joules per Kelvin times moles. And for this, pressure has to be in pascals and volume has to be in meters cubed. Okay, so just bear that in mind. If you use that value for R, the 8.3145 joules per Kelvin mole, you gotta have pressure in pascals, volume in meters cubed. Anyway, there are other values you can find. It doesn't matter which value you use. The most important thing is you have to match your units for pressure and volume to your units for the gas constant. So this is liters and atmospheres. So that would mean I would have to use liters and atmospheres for my pressure and my volume. That's the key, is you got to match the units on both sides of the equation. And another thing about the R, they're just units. So it's 0.08206 liters times atmospheres divided by Kelvin times mole. I don't know why, but some students think it's like a tiny little equation inside of the equation, and they want to plug their volume in here, they plug the pressure in here, they plug the, no. Those are just the units, okay? Just leave them like that. All right, so let's talk about the other gas laws really quickly. I'll give you a little table kind of outlining all those other gas laws. And then in the next video, we'll probably do some examples. Now, the other gas laws allow you to calculate something from initial conditions to final conditions, which is different from the ideal gas law, but we'll talk about that. So we'll have the law here, the name of it. And this is going to be kind of strange, but it'll say volume is proportional to whatever's there. What is constant? I'll explain all this. And then the typical equation that you're given. So start off with Boyle's law. In Boyle's law, volume is proportional to 1 over pressure. That means volume is inversely proportional to pressure. Oops, I misspelled proportional up there. Proportional to. So what does that mean? That means if volume goes, if pressure goes up, then volume goes down. So if you take a balloon and you squeeze the balloon, you put pressure on the balloon, then the volume will become smaller. That makes sense. Okay, what is constant? And when I say what's constant, if we look at PV equals nRT, okay, over here, we've talked about volume and pressure. Volume and pressure. Everything else is constant. So what's constant in PV equals nRT? I'm sorry, in Boyle's law? N and T. R is always constant, so we don't worry about it. So N and T are constant. And then the equation relates pressure to volume. So P1 V1 is equal to P2 V2. There's the equation. All right, next up, we have Charles's law, and you do not need to memorize the names of these, okay? That's just how they're referred to, so I am referring to them that way, just like the text. Okay, volume. For Charles's law, volume is proportional to temperature, and volume is always proportional to temperature. It's not just for Charles's law, but that's what Charles's law deals with, volume and temperature. So when temperature goes up, volume goes up. When temperature goes down, volume goes down. Blow up a balloon, stick it in the freezer. It'll get smaller. Okay? And what is constant in Charles's law? Moles and pressure. And Charles's law says V1 over T1 is equal to V2 over T2. So the 1 and the 2 in this, you can think of this as initial, the ones, and then the final. And we'll do an example in another video and it'll make more sense. So the 1 is the initial conditions, 2 is final conditions. It doesn't really matter. You just got to keep everything straight and don't mix up like the volume and temperatures for 2 different parts of the problem. All right, and then Avogadro's law. Wow, having some trouble with this one. Avogadro, there we go. You can probably guess this has to do with N, number of moles. The volume is proportional to N, the number of moles. That just means that if you have more moles, the more moles occupies a larger volume. So take a balloon, blow some more gas or air into it, and it gets bigger. Okay, and then what is constant? Pressure and temperature are constant. And Avogadro's law, V1 over N1 is equal to V2 over N2. All right, and there are other gas laws. Okay, there's lots of other gas laws. Well, maybe not lots, but there's a few other gas laws. So we can rearrange PV equals nRT into any gas law we want because it has all the variables there. Pressure, volume, moles, R, of course, and temperature. So let's just say that we want a gas law that relates, well, let's just say we're trying to find, remember what Charles's law was, okay? Charles's law up here, volume and temperature, okay? But we don't remember if it's V1 over T1 or V1 times T1. We're just, having one of those moments where we can't remember, can't find it on our notes. So if we want volume and temperature, those are our variables. Okay, and what does that mean? That means everything else is constant. These guys, the green ones, are constant. So what we're going to do is rearrange the ideal gas law to get the constants on one side and the variables on the other side. So I'm just going to write everything over again. PV equals nRT. Okay. And now I'm just going to divide both sides by P, divide by P. So we get V is equal to nRT over P. And now divide by T, or just multiply by 1 over T, same thing. And we end up with Charles's law. Or I'm sorry, what we end up with is something that looks like Charles's law. V over T is equal to nR over P. Well, remember, we said that this whole side is constant. That's constant, so V over T is equal to nR over P, which is equal to V over T. I know that seems kind of silly, but what we can say is if the number of moles don't change and the pressure doesn't change for a gas, then what we can say is V1 over T1 is equal to V2 over T2. Okay. Again, those things have to be held constant for this to work. Okay. R is always constant, so it doesn't really matter. All right, that's enough for the gas laws.